Hi everyone, today I'm gonna talk about transport layer part 2. Let's talk about outline. Introduction, transport layer protocols, user datagams protocols, transmission control protocol. Let's talk about objectives. We introduce general services we normally require from the transport layer, such as process-to-process communication, addressing, multiplexing, error flow, and congestion control. We discuss general transport layer protocols, such as stop and wait, go back in, and selective repeat. We discuss UDP, which is the simpler of the two protocols we discussed in this chapter. We discuss TCP service and feature. We then show how TCP provides a connection-oriented service using a transition diagram. Finally, we discuss flow and error control and congestion control in TCP. The transport layer protocols. We create a transport layer protocol by combining a set of services described in the previous sections to better understand the behavior of these protocols. We start with the simplest one and gradually add more complexity. Simple protocol. Our first protocol is a simple connectionless protocol with neither flow nor error control. We assume that the receiver can immediately handle any packet received. In other words, the receiver can never be overwhelmed with an incoming packet. In Figure 3.17 shows the layout for this protocol, FSMS. This is the figure 3.17. Simple protocol. And this is figure for FSMS for this simple protocol. Figure 3.19 showed an example of communication using this protocol. It is very simple. The sender sends packets one after another without even thinking about the receiver. For the example, example 3.3. Stop and wait protocol. Stop and wait protocol. 1 second protocol is a connection-oriented protocol called the stop and wait protocol, which uses both flow and error control to both the sender and the receiver use sliding windows of size 1. The sender sends one packet at a time and waits for an acknowledgement before sending the next one. To detect corrupted packets, we need to add a checksum to each data packet. When a packet arrives at the receiver side, it is checked. Continue. We have many topics. The first one is sequence number, acknowledgement number, SMS sender, receiver, efficiency, and Pipelining. Stop and wait protocol. This is a SSM for the stop and wait protocol. The figure 3.22 shows an example of the stop and wait protocol. Packet is sent and acknowledged. Packet 1 is lost and resent after the timeout. The resent packet 1 is acknowledged and timer stop. Packet is sent and acknowledged, but acknowledgement is lost. The sender has no idea how the packet out and acknowledgement is lost, so after the timeout, it resends packet 0, which is acknowledged. It's bold again for example 3.4. Assume that in the stop and wait system, the bandwidth of the line is 1 megabyte per second, and one bit takes 20 milliseconds to make a round trip. What is the bandwidth delay product? If the system data packets are 1000 bits in length, and what is the utilization percentage of link? Is a solution for this question. The bandwidth related product is 1 to mega. Mega is equal 1 power 6, and multiple 20 and multiple 10th power minus 3 is equal 20,000 bits. The system can send 20,000 bits during the time it takes for the data to go from the sender to the receiver and the acknowledge to come back. However, the system sends only 1000 bits. The link utilization is only once divided by 1000 divided by 20,000, it means 5%. If what is the utilization percentage of the link in example P25, if we have a protocol that can send up to 15 packets before stopping and worrying about acknowledgement, there's a solutions about it. So 15 packet also 15,000 bits during a round trip. That means it's mean 75%. Of course, if the damaged packet utilization percentage is so much less because the packet have to be resent. Go back in protocol. To improve the efficiency of transmissions, multiple packets must be in transition while the sender is waiting for the acknowledgement. In this session, we discussed one protocol that can achieve this goal. In the next section, we discuss the second. The first called Go Backend. The results for the name will become clear later. So to continue, sequence number, acknowledgement numbers, sends window, receives window, timers, resends packet. And as well as sender, receiver, send window size, go backend versus stop and await. This is the figure for go backend protocol. This is sliding the sense window. Receive window for go backend. FSMS for the Go backend protocol. Then Windows site for Go backend. Figure 3.29 shows an example of Go backend. This is an example of a case where the forward channel is reliable, but the reverse is not. No data packets are lost, but some acts are delayed and one is lost. This example also shows how cumulative acknowledgements can help if acknowledgements are delayed or lost. Show diagram for example 3.7. Figure 3.30 show what happens when a packet is lost. Packet 0s 1, 2, and 3 are sent. However, packet 1 is lost. The receiver receives packet 2 and 3, but they are discarded. Because they are received out of the order, packet 1 is expected. When the receiver receives the packet 2 and 3, it sends X1 to show that it expects to receive packet 1. However, these X are not useful for the sender because the X node is equal to FF not greater than FF. So the sender discards them when the timeout occurs. The sender resends the packet 1, 2, and 3, which are knowledge. Further diagram for example 3.8. Selective repeat protocol. The Go backend protocol simplifies the process at the receiver keeps track of only one variable, and there's no need to buffer out of other packets. They are simplified discarded. Another protocol called the Selective Repeat (SR) protocol have been devised, which, as the name implied, resent only selective packets. Those that are actually not lost. The outline of this protocol is shown in the figure 3.31. Windows Timer Acknowledgement (FSMS). Sender receiver outline of selective repeat. Send window for selective repeat protocol. SMS for SR protocol. Assume a sender sends a 6 packets, packet 0 to 5. The sender receives an ACK, which ACK node equal 3. What is the interpretation if the system is using GBM or FR? So if system using GBM, it means that packets 0, 1, and 2 have been received uncorrupted, and the receiver is expecting packet 3. If the system is using FR, it means that the packet 3 have been received uncorrupted. The ACK does not say anything about the other packet. This example is similar to example 3.8, the figure 3.30, in which packet 1 is lost. We show how selective repeat behavior. In this case, the figure 3.35 shows the situation at the sender packet 0 is transmitted. The acknowledged packet 1 is lost. The packet 2 and 3 write out of order and are acknowledged. When the timer out packet 1's only unacknowledged packet is resent and acknowledged, the sent window then sliced. Example 3.10. At the receiver side, we need distinguish between the existence of the packets and its stability to application layer. At the second write, packet 2 writes and this stored and mark shattered slot. But it cannot be delivered because the packet 1 is missing. At the next arrive, packet 3 arrives and is marked and stored, but still not all of the packets can be delivered, only at the last arrive. When finally a copy of packet 1 arrives, can packet 1, 2, and 3 be delivered to the application layer? There are two conditions for the delivery of packet to the application layer. The first set of concentration packets might have arrived. The second, the set start at the beginning of the window. The photo again for example 3.10. Selective repeat window size. Bidirectional protocols. The four protocols we discussed early in this section are all unidirectional. The data packet flow in the only one direction acknowledgement rather in other direction. In real life, data packets are normally flowing in both directions, from client to server and from server to client. This means that the acknowledgement also needs to flow in both directions. A technique called piggybacking is used to improve the efficiency of the bidirectional protocol. Design the piggyback in Go backend. It's the figure 3.37. Internet Transport Layer Protocol. A network is an interconnection of the sets of devices capable of communication. In these definitions, a device can be a host such as a large computer, desktop, a laptop, a workstation, cellular phone, or security system. And this definition can also be connecting devices such as a router, a switch, a modem that changes the form of data, and so on. The figure 3.38 position of transport layer protocol in TCP/IP protocol suite. And some well-known port used in UDP and TCP. Okay, just the last page about summary. We discussed several common transport layer protocols in this chapter. The stop-aware protocol provides both flow and order control, but it's inefficient to efficient. The go backend protocol is more efficient version of the stop-and-wait protocol and take advantage of the pilingering. The selective repeat protocol and modification of the go backend protocol is better suited to handle packet loss. Although this protocol can be implemented bidirectionally using a piggybacking.